Hey, hello and welcome back, everybody. Moving on to the second subsection, really, in our common rules of the continuous integral, integration by parts. So this is probably a new technique to most of you. It can be covered in some Calculus 1 courses. It could be covered if you took, high school calculus and they tried to cover AB and BC exams. Even in my high school calculus, way back when I took it, we did cover integration by parts, even though I was only studying for the AB exam. But really what this is if we jump back to our previous video, integration by substitution was the opposite of the chain rule. Integration by parts is the opposite of the product rule. Right, so we're just kind of going to undo the idea of the product rule, which if I throw it out here, I take the derivative of a product of two functions. What do I get out of that? Well, I get f prime times g plus g prime times f. And if I want to undo this, what's going to happen is I'm going to remove the derivative on the left-hand side and include an antiderivative on the right-hand side. What's kind of the downside to integration by parts, or how does it differ from the regular product rule, is you'll notice we really have two terms here inside of our integral. So there's kind of two sets of multiplications added together. And unfortunately, that's not the way most integrals are shown to us, right? When we see an integral, we normally only see a single integrand. And so what actually happens when we undo this is we distribute our integral to both terms here, and we bring one of them to the left-hand side. So when I distribute that integral to both terms, I really have the integral f prime times g dx plus the integral g prime times f dx. And suppose I was originally trying to compute maybe this particular antiderivative. I don't know what it's equal to. I mean, I know it's equal to the multiplication of the two functions together, but there's kind of this extra term that originally wasn't included in the antiderivative. So I'm going to bring this to the other side. And what integration by parts is actually saying, if I rearrange everything now, it says that the antiderivative of f prime times g dx is equal to, so that's this term that I've highlighted. So what's that going to be equal to if I bring the other term from the product rule to the left-hand side? Well, it's going to be equal to the product of the two functions, f times g. And then when I bring the second integral to the left-hand side, it's going to obtain a negative sign, so minus g prime x times f of x dx. So this statement that I've just constructed really is our integration by parts statement. The way I describe it in the proposition is going to make a little bit more sense as in terms of how we're actually going to use integration by parts. But what we want to think about with integration by parts is there's an integral of a product of two functions. This is another reason of thinking about it as the opposite of the product rule. So taking the integral of a product of two functions, what we get out of it is, well, still a product of two functions, but then minus another integral of a product of two slightly modified functions. And in some sense, this should make our lives easier, but we'll see how it makes our lives easier later. So the proposition, the way I phrase it here is very slightly different. I say that we rearrange, we don't actually compute integrals. Okay, so if integration by parts is really a technique of rearrangement, not necessarily computation. So if I have the integral of a product, so here I've got f and g, I can rearrange that integral into two terms. Now what's going on with these two terms is I end up with a product of the antiderivative of f with g as the first term, and then I have something like minus the integral of the antiderivative of f times g prime. So it's an antiderivative of f, but it's a derivative of g. And this is supposed to make our lives easier, specific in the case where, well, number one, I can actually compute the antiderivative of my first term f, but more importantly, it makes my life easier if this g prime ends up being easier, or maybe a more simple function than the original function g in the integral. And a good case of that is polynomials, right? Because if I think about it, something like when g of x is equal to x, I've got f times x, or f times g of x, but if I take the derivative of g, what do I end up with? Well, I end up with g prime, which is just 1. And 1 is a very simple function, especially if it ends up being inside of an integral multiplying a term. So by taking derivatives of at least one of the two terms in integration by parts, it's supposed to make my life easier. I have the proof here. It's actually the same proof that I went through right away at the beginning of this video, so we're not going to go over that again. I do have, this line here, which is kind of what I mean to say, which is what would actually make this useful is when we can compute the antiderivative of, now there's really two antiderivatives going on, right? Because there's an antiderivative there, but capital F was already an antiderivative. So there's kind of two antiderivatives happening. But why would the antiderivative of f times g prime, and then an antiderivative of all of that, be easier than computing maybe my original integral, which is just lowercase f times lowercase g? Well, this specifically gets easier when g prime is a simpler function than g. And we also kind of require that we can actually compute this capital F. So I do say that the antiderivative of lowercase f is actually, computable. It's something you know how to do. But we're really looking for this one piece, g prime, being simpler than g. So what are the cases that makes this happen? Well, there's an acronym for it. Unfortunately, it's not a mnemonic or anything because this word is just kind of ugly. LIATE. I just think about the word late. Throw an I in there. I don't really know why it was used, but it's easy enough to remember once you look at it and you convince yourself LIATE is what you should remember. And so this acronym gives you kind of an ordering. It provides an ordering for choosing functions which get easier under derivatives. And what does this ordering look like? Well, we start with logarithms, and why would that be the case? Something like d dx of log x is 1 divided by x. And this is often the case because this 1 divided by x will turn around and multiply a polynomial, and all it does is reduce the degree of the polynomial by 1. And so that definitely gets easier when you take a derivative. If I look at inverse trig functions, classic example of this would be maybe arctangent, where I know when I take a derivative of arctangent, I get 1 over 1 plus x squared. So even though it started as an inverse trig, it kind of ended up, these are called rational functions, where you kind of have a ratio of polynomials. So it ended up just as a ratio of polynomials. So the fact that we're kind of translating trig functions into polynomials, that's made them simpler, right? The next case is these algebraic functions. These are, rational or polynomial functions, or square roots of polynomial functions. Those are going to be your algebraic functions, and they get easier just because derivatives reduce the order of a polynomial, right? A derivative is going to take x cubed to 3x squared. Trig functions don't really get any easier, which is why we save them for the end. Something like d dx of sine becomes cosine. Cosine's not really any easier than sine, so that's kind of why these are pushed towards the right-hand side. They don't get any easier. And the same idea with exponentials. If I take d dx of e to the x, well, of course, it's just itself, right? So absolutely nothing changes if you take derivatives of exponentials. So they're not getting easier at all. And even in the case of something like d dx e to the x squared, now you're getting, 2x e to the x squared. So actually, your life has gotten harder by taking derivatives. So we really, if we can avoid it, we almost never consider these two. Now, unfortunately, we're going to see cases where we cannot avoid it, and we do actually have to consider those two. So with that said, let's actually, I'm gonna highlight the actual statement once again, and then we'll try an example. So the statement says, I'm gonna have two functions multiplied together underneath the integral sign. I want to choose g according, I'll say choose according to LIATE, okay? And then we just go ahead and actually compute the right-hand side. And the right-hand side is gonna be the antiderivative of f times g minus the integral of the antiderivative of f times g prime. When we look at our example now, we have a multiplication of x times sine x. So this is a classic example of me just multiplying, in the first case, an algebraic function times a trigonometric function. And so according to LIATE, which one comes first, algebraic or trigonometric? Well, there's my algebraic. So I'm going to go ahead and choose the algebraic function to be g of x, which means my integration by parts formula, which I have at the bottom here. I'm just going to swap out g of x with my x. I'm going to swap g prime with, well, what's the derivative of x? Thankfully, it's just 1. If I've chosen g of x equals x, well, that means that f of x has to be what's left over. F of x is sine of x, which means here and here I'm going to need an antiderivative of sine. So let's go ahead and compute that antiderivative of sine as negative cosine. And I do mention it's quite all right to not include the plus c at these antiderivative stages. It's just going to get in the way if we include them. So just drop your plus c's when you're computing these capital F's. So we have that capital F is negative cosine of x, which means at these two places, I'm going to replace capital F with negative cosine x and negative cosine x. When I make all of those swaps, what do I get? I get that, my integration by parts has now given me negative cosine x minus the integral of negative cosine x times 1. And this integral is fairly easy to actually compute because I've kind of simplified the multiplication by x over here to just a multiplication by 1 over there. Now, a lot of students will make the mistake. We've got a minus sign that's coming for free from integration by parts, so we always have to remember that minus sign in integration by parts. And the capital F has given us another minus sign, so we have to be careful and combine these together into the plus sign that you see below. So when I simplify everything, those two minuses are going to simplify into a plus, and I end up with that my answer is negative x cosine x plus the integral of cosine x. And we know how to integrate cosine x. Just go back to the table. We find out that that is equal to sine of x. So it turns out that the overall integral, the original one we wanted to compute, integral x sine x dx, is equal to negative x cosine x plus sine x plus c. That's kind of the classic case of integration by parts. Unfortunately, it's really only going to be done after one step if that is a polynomial to the first power, or a linear function, right? Mx plus b is your multiplicative term. In every other situation, you'll probably have to go through multiple rounds of integration by parts. And so we see in this case, we have a quadratic, which is kind of our multiplicative algebraic function times an exponential. And let's just recall with Lyate that algebraic times exponential. When I look at Lyate, I definitely recover the algebraic far before my exponential, so we're going to choose that the algebraic function is g of x, which in our case, what is our algebraic function? It's x squared plus 2x, which means its derivative, g prime of x, is going to be 2x plus 2. And that's what we see down here, g prime of x is 2x plus 2. Now, it does mean our function that we're not going to take a derivative of, but rather take an antiderivative of, will be e to the negative x over 2. So how do I actually take an antiderivative of e to the negative x over 2? Well, we can do this with a quick substitution. So we'll call negative x over 2 the variable u, which means that du will be negative dx over 2, or rather that negative 2 du is equal to dx. So I can replace the dx with negative 2 du, and we just have the antiderivative of e to the u, which we know is e to the u. And as before, it's totally fine to not include plus c at this stage. And so we end up with the antiderivative of our lowercase f is negative 2 e to the negative x over 2. So now I've calculated, well, I've defined lowercase f, I've defined lowercase g, I've computed uppercase f, and I've computed g prime. I can use all four of them in the integration by parts formula. And what this gives me is, here's capital F, here's g, here's capital F yet again, and here is g prime. And if we simplify a little bit, right, I can go ahead and take that minus sign, combine them into a plus, as well as the 2 here can come out front. I rearrange some other terms. But what we end up seeing, this is where I'm saying it sometimes becomes unfortunate, is we're left over with a term, which is an integral times a product of functions. So I've got an integral of a product of functions here. That's an algebraic function. That's an exponential function. So what do we have to do? We do it again. It being integration by parts in this case, because this algebraic function will finally simplify. We're going to take a derivative of that function again, take a derivative of 2x plus 2, what we'll end up with just 2. So by taking one more derivative, this will simplify down to a constant, but unfortunately it takes us 2 rounds. So let's analyze that latter integral just on its own, and we'll do it as an integration by parts again. So we're going to call this lowercase g, we're going to call this lowercase f, and as before, capital F is going to be the exact same function. In this case, lowercase g prime, I take a derivative of 2x plus 2, I just get 2, thankfully. So I define f, I define g, I compute capital F, and I compute g prime, and I plug all 4 of them in to the integration by parts formula. What do I end up with? I end up with negative 2 e to the negative x over 2 times 2x plus 2 minus the integral of, this is capital F, what I've just highlighted, and then we're left over with this is g prime. And so in computing integration by parts one more time on this latter integral, we simplify everything a little bit, and we bring our terms out front there. We've got negative 2 times 2, so I have a plus 4 here, and then we just have this final integral of e to the negative x squared over 2, which lo and behold is exactly what we've been integrating this entire time. And so we just have one more copy of this capital F there, which is negative 2 e to the negative x over 2. And so we're going to replace that term with that final case of its antiderivative. That's what I've done right here. And I go ahead and simplify everything by distributing that 4 to the negative 2. It's going to give me a negative 8. And in fact, now I have negative 8 e to the negative x over 2, as well as a negative 4 e to the negative x over 2 here. So I have negative 12 copies total of the e to the negative x over 2. So that's going to be just the computation of the ladder integral, where now if I jump all the way back to where I was at the beginning, we had already computed this term, but we hadn't yet computed this ladder integral, which I did just finish. So now I'm going to substitute this ladder integral in. And once I substitute it in, here it is, which I've just computed as this value. I can substitute that in and distribute my 2 to both terms, this negative 4 and negative 12. That's giving me a negative 8 and a negative 24. Notice every single term here has an e to the minus x over 2, so I can combine these polynomial terms together. I have negative 2x squared minus 12x minus 24 e to the negative x over 2 plus c. So this is what 2 rounds of integration by parts ends up computing. Unfortunately, integration by parts ends up even being trickier than just repeated integration by parts against polynomials. It's very algorithmic to do it repeatedly against polynomials. There's a couple cases where you can't be quite so algorithmic. And this comes down to some of those cases that I was mentioning earlier. There's a product of an exponential function times a trigonometric function. So here I've got exponential times trigonometric. And if we go back to Lie 8, exponentials here and trigonometrics there. So we're going to make a choice on the trigonometric as g of x, but it's not going to be a pretty choice. We're going to run into a little bit of difficulty here. So let's go ahead and do it and just see what happens, because there's a trick here. That's what I mentioned here, trick. There's a trick that's going to happen in the next 3 problems that we do have to pay a lot of attention to, because this is what can really trip students up in integration by parts, is recognizing these tricks. So there's a g of x. Because of Lie 8, I'm going to assign cosine of 2x, and it's not too hard to compute its derivative, right? Using the chain rule on cosine, derivative of the outside is negative sine. I'm going to keep the inside the same, and I'm going to multiply by the derivative of the inside. So I have negative 2 sine 2x. Not too bad. And in fact, it's not even hard to compute the antiderivative of what we're going to call f of x. That's just going to be the antiderivative of e to the negative x, which, if we go through a u substitution, is just going to give us a negative sign because of that negative x there. So we'll end up with negative e to the negative x, and go ahead and omit your plus c. So it's not even hard to compute this capital F of x as negative e to the negative x. What kind of makes it disheartening is if we compute our 4 terms that are useful in our integration by parts. There's f, g, capital F, and g prime. It's disheartening because when we plug all 4 of those into our formula, well, what do we end up with? This term's fine, whatever. Negative e to the negative x, cosine 2x, whatever. If I go ahead and simplify this ladder integral, what does it simplify into? Well, it simplifies the negative 2 here, a negative and a negative, so 3 copies of negatives. That pulls out front just fine, negative 2, whatever. We look at the actual integral that results. We have integral e to the negative x sine 2x dx. This has quote-unquote simplified, which is just not true, but it's at least turned into a product of an exponential and a trig function, which is the same thing we started with. We've basically gone nowhere in terms of an integration by parts, and yet, this is one of those cases of a trick. I'm telling you, you just have to do it again, and trust me that it's going to work out, and hopefully by seeing enough of these tricky problems, you're able to recognize it for yourself. So we're going to do it again, just like we did before, and we're going to see what happens. We're going to do one more round of integration by parts with an exponential against a trig and see what happens. So we've got this integral here, e to the negative x sine 2x dx. Just as before, Lie 8 is telling us that we're going to choose the trig function before the exponential function. So we go ahead and choose g of x is sine 2x. That's going to give me g prime as 2 cosine 2x. We choose f of x as e to the negative x. As before, that's going to give me capital F as negative e to the negative x. And, lowercase f and lowercase g are coming along for the ride. If I substitute all 4 of those definitions into my integration by parts, what do I end up with? Well, I end up with, here is capital F times g minus the integral of capital F times g prime. Let's go ahead and simplify that. It simplifies, well, there's this term out front. We're not too worried about that term out front. It's been computed. I've got negative 2 here, so the negatives cancel to a positive 2 out front, and my final integral I'm left with is the integral e to the negative x cosine 2x dx. Everybody's looking at me like, we're back where we started, Evan. Nothing has changed. How do I actually integrate this? It's a product of an exponential and a trigonometric function. This is the trick. The trick, if I look in particular at this final integral is the same integral we started with. And what do I mean by started with? I mean all the way back at the beginning of this problem. If I jump all the way back to the beginning of the problem, integral e to the minus x cosine 2x dx. That's what I would like to compute. If I go all the way back down here, 2 rounds of integration by parts, integral e to the negative x cosine 2x dx. So that means there's really 2 copies of this term I'm searching for sitting around my problem. Now, let's keep in mind what this entire term is. This entire term is just the latter integral from the first integration by parts, right? So this term that I'm circling right now, if I scroll up to here, which was my first round of integration by parts, that piece I just computed is just this integral. So if I go and try to bring everything together, what have I actually computed using 2 rounds of integration by parts? Well, I've computed that what I was originally looking for is equal to, this is the first thing I computed, minus 2, and then I had that second integral that I wanted to compute. I went through the work to compute that second integral, and I ended up with 2 terms in there. If I go ahead and distribute this minus 2 to both terms here and here, I can do that. I'm going to simplify that just a little bit. What do I have? I have the integral of e to the negative x cosine 2x dx equals negative e to the negative x cosine 2x plus 2 e to the negative x sine 2x minus 4 integral e to the negative x cosine 2x dx. This is what 2 rounds of integration by parts has accomplished. But this very last integral is the same as the very first integral. What does this mean? If I give this integral a name, let's call it capital J. Let me give it the name capital J. That means I can give this integral a name, capital J. And once I have an equation where there are some capital J's sitting around and some other terms, but capital J is what I'm looking for, all I have to do to finish solving a specific problem is to solve the equation for capital J. I can do that because it looks like all I have to do is add 4 copies of capital J to both sides. That's going to end up with a 5 on the left-hand side, right? If I add 4 copies to both sides, I'll have a 5 on the left-hand side. The negative 4s are going to cancel each other on the right. And so we end up with 5 copies of the thing we were originally looking for is equal to this computation that I've provided here. Well, 5 copies of what we're looking for is equal to the computation. Divide both sides by 5, and we know that 1 copy of what we're looking for is exactly 1/5 of the computation we had before. And at this point, you see everything's finished. I mean, I guess I could add a plus c onto the end of this to be precise. But aside from that, that integral's been computed. And it feels like magic. It kind of was created out of thin air because we rearranged the right-hand side twice to see that it was equal to itself in a specific way. But once you know it's equal to itself, you can solve for it, right? This is exactly what something like x equals x squared minus 1 means. Is like, you've got 2 copies of x sitting around. You should be able to rearrange this so that there's only 1 copy of x on a specific side, and that you've actually found what you're looking for. And so this is that trick, or really one of multiple tricks with integration by parts, which professors like to throw at you to see if you really understand what's going on with integration by parts. So we'll have a lot of examples of doing this in our exercises, but it is something to keep in mind that it's just not an easy thing to wrap our heads around. Unfortunately, there are more tricks that I'm going to go through right now. So the next trick that integration by parts can give us regards the antiderivative of the natural logarithm. Right, it's probably an antiderivative none of you were asked to compute in Calculus 1, even though it seems like a very natural question to ask. What is the antiderivative of log? Well, you're not asked to compute it because it really is a case of using integration by parts. But what's really weird is that there's no product of functions here. And when I say there's no product of functions, how in the world am I supposed to use integration by parts, also known as the product rule for integration? Well, it's because there is a product of functions. All the time when we write something down in math, not just when we're trying to do some fancy integration by parts, there are actually always infinitely many multiplicative ones. Against any mathematical, I guess technically numerical expression that we write down, you can put infinitely many, technically arbitrarily finitely many multiplications by 1 against that object. And so this log, which is written as log x, is actually log x times 1 times 1 times 1. And once you even remark about a single product with a 1, it turns out there is a product of functions. It's been hiding in plain sight. It's the product of the log of x with the function 1. And the function 1, at least as so far as liate is concerned, is a polynomial, right? I write down any constant. It's a 0-degree polynomial. So 1's algebraic. Log x is, of course, logarithmic, which means Lie8 is telling me g of x should be my logarithmic function, which means f of x should be my constant function 1. Well, what does that mean if I'm going to use integration by parts? Well, g prime can be computed as the derivative of log, which we all know is 1 over x. And capital F can be computed as the antiderivative of 1, which we all know is x. And so now I've established g prime f, and capital F. And I can go ahead and compute integration by parts using f, g, capital F, and g prime. If I plug all 4 of those in, what do I actually see? Well, here is capital F, g, minus capital F, g prime. What's actually happened in that second integral is I have an x times a 1 over x. Those are going to cancel, and this is equal to the integral of 1 dx, which we just know as x. And so it works out, we've got x log x minus x here, x log x minus x plus c. And so that's how you actually compute the antiderivative of the natural logarithm. Really fascinating to see. I'll provide one more example here of kind of this trick. And that's with the inverse tangent function. I actually ran this on my last semester's Calculus 2 exam and stumped probably 90 to 95% of my students, which was unfortunate. It means I didn't express this multiplication by 1 quite strong enough. And so the inverse tangent function, right, if that shows up in Lie8, it's definitely there. And if you're stumped on how to integrate something, it's probably integration by parts by multiplying by 1. Very fancily. So we've got Lie8 sitting around here, and inverse trig is the second case. If I do the same thing I did before where I multiply by 1, 1 is of course algebraic, and so we're going to go ahead and include this multiplication by 1, but we're going to call the 1 f of x, and we're going to call tangent inverse g of x, which means what? G prime is the derivative of tan inverse. Go back to your derivatives chart if you want to see what this is equal to. It's 1 over 1 plus x squared. And what is the antiderivative of 1? Well, everybody remembers that one. It's just x. So there I've computed f, g, g prime, and capital F. And so I have them down here, f, g, capital F, and g prime, and I'm going to include them in my integration by parts formula. What do I get out of this? Well, here's capital F, here's g, minus the integral of capital F times g prime. It looks like this may not be able to be integrated, but when I simplify this a little bit, what am I looking at? I'm looking at the integral of x over 1 plus x squared dx. That should kind of be screaming as a natural choice of integration by substitution, because what is the derivative of that denominator, 1 plus x squared? Well, the derivative of 1 plus x squared is just 2x, and my numerator x is a multiple of that. And so it really does look like, you know, a function in parentheses times its derivative. And so we have a substitution in that second case. I'm going to go ahead and choose, like I already kind of mentioned, u equals the denominator, 1 plus x squared. So that du is 2x dx, or if I'm looking at my x dx and I say I'd rather just have x dx there, let's divide both sides here by 2, so that cancels, and I just have a 1/2 du in terms of my x dx, and my denominator, 1 plus x squared, can just be replaced with u. Now we're looking at 1/2 times the integral of 1 divided by u. The integral of 1 divided by u is log of u. So I have 1/2 log u plus c, or in other words, 1/2 log 1 plus x squared plus c. That's going to be the integral of x over 1 plus x squared. Well, what that means is that this original integral I was trying to compute, the integral of arctangent dx, is actually equal to x tangent inverse minus the integral of x over 1 plus x squared dx, which we just computed. And so we have the integral of arctangent is equal to x arctangent minus 1/2 log 1 plus x squared plus c. So never forget, if you're really stumped on an integral, multiply it by 1 and apply integration by parts. It may get you somewhere. It may not get you somewhere, but it may. And so we're going to finish actually by a proposition, and this proposition really has been a combination of the last two cases we saw. It's a proposition where we're going to compute the arbitrary integral of an inverse function, right? If we have the ability to compute the antiderivative of like the forward function, right, the antiderivative of f without an inverse on it, if we can compute that, then actually we can use integration by parts to compute the antiderivative of the true inverse function. Now, how do we do that? We have a few choices for doing this. The nicest proof combines both substitution and integration by parts, and I'll show you how that works right now. So let's just start with our integral of f inverse of d of x, and let's say, for some strange reason, we're just going to immediately choose to do a substitution of u being f inverse. So we're just going to use integration by substitution and say that's going to be my expression for u, which means it's easy enough to invert that expression and say, okay, well, that just means x is actually f of u. Well, if x is f of u, we can compute dx, this final term on the integral, just by computing a derivative of f of u, which of course is just f prime of u, du. So that's what we're going to swap in for dx, f prime u du, and of course we've chosen to make this the substitution variable. So by substituting both of them in, it turns out the antiderivative of f inverse dx is the same as u f prime of u du. But something like u f prime u du is a multiplication of functions where in particular that u is algebraic. Now we don't really know what f prime is equal to, but what we do know is that it's pretty easy to take an antiderivative of. So it's not a bad idea to take a derivative of u and an antiderivative of f prime, because the antiderivative of f prime is just f. So we're going to go ahead and choose that u is equal to g of x, and f prime, now this is a little bit confusing, f prime is equal to our version of f of x, but that's just to say that we need to compute its antiderivative, which is going to be f. So if we apply an integration by parts to the substituted version, u f prime u du, well, here's g times capital F minus capital F times, well, what is g prime of u is just 1, so there's a times 1 hiding in there. And we know what the antiderivative of lowercase f is, at least the way we've defined it. We've just defined it to be capital F. And these are all in the variable u, and u, which was our original substitution variable, notably f inverse. And so by plugging f inverse in for every single case of u here, what do we actually end up with? Well, f and its inverse cancel. That's specific to that section there. And what are we left with? We're left with x, f inverse, minus the antiderivative of the forward function evaluated on f inverse, plus some constant. So that's a nice little rule that actually could have given that inverse tangent and natural logarithm functions for free, right? Because the natural logarithm is the inverse of the exponential, and we know how to take the antiderivative of the exponential. Could have given that for free. Of course, arctangent is the inverse of tangent, and we do know how to take the antiderivative of tangent, at least if you go ahead and look at the table that I shared. Anyway, that's all I've got. We're going to work with combined rules and intuition in the next section. So it's going to be a lot of work in the next section. I know this was a lot of work too. Let's do some exercises together and hang in there. It's going to be a good time. See you then. Bye.